This video goes through the process for deriving the geodesic equations for particles moving in a Schwarzschild space-time. It reviews the meaning of the parallel transport of a vector and shows how the geodesic equation is derived from the forward velocity of a particle. It then uses the parallel transport of the forward velocity vector combined with the symmetries expressed by Killing vectors to derive expressions for the motion of a particle with mass. Alright, so geodesics are paths taken by freely falling particles or objects as they move through space-time. And the term freely falling just means the motion of the object is determined by gravity alone. In other words, how the object moves is determined by the curvature of space-time. The actual path taken by an object in space-time is its world line, which can be expressed as a 4-vector where each component is parameterized in terms of some affine parameter lambda. And the components for this 4-vector x mu are shown here, the time component and the 3 spatial ones. In the case of a particle with mass, this affine parameter is the proper time of the particle as measured by a clock it carries with itself. This parameter can also take the form m times tau plus n, where m and n are constants. Right. This parameter cannot be used for massless particles such as photons since d tau equals 0. Since ds squared is minus c squared d tau squared, distance travelled by light is 0, and so we have to use lambda, some other parameter. We can't use proper time. Now, geodesics are the straightest possible lines in curved space, and they parallel transport their own tangent vectors, just as straight lines in Euclidean space parallel transport their own tangent vectors. So let's say we have a tangent vector as a function of the parameter, the affine parameter lambda, and then we differentiate with respect to lambda of the position 4 vector, this object here, and that is our tangent vector. And the condition for parallel transport, which we'll investigate shortly, is the total derivative of the tangent vector with respect to the affine parameter lambda is 0. Now, parallel transport means the tangent vector is moved along the particle's world line parallel to itself in very small steps or infinitesimally small steps, and where its direction and magnitude are held constant. There are other videos on this, on parallel transport on this channel, so have a look at those. Alright, the tangent vector to a particle's world line is its forward velocity, u superscript mu. And the tangent vector components, t mu is dx mu d lambda, u mu, that's just the components. And if we have a look at this manifold here, this two-dimensional surface representing our space-time manifold just reduced to 2 spatial dimensions, just for visualization purposes, nothing more. Here's our world line in blue, the position 4 vector given here. Here's our tangent vector that exists at each point on that curve, on that world line, each point. And the components of that tangent vector, u mu, are these 4 here, the time component and the 3 derivatives of the spatial components here. This is the derivative of the time component as well, sorry. And again, reminding you, the condition for parallel transport of a vector, in this case the tangent vector, which is the forward velocity of the particle, is dt d lambda, lambda the affine parameter, so it's the total derivative of the tangent vector, and that's equal to 0. And that's the condition for parallel transport. Now, particles with mass travel along a time-like world line, which means that the square of the magnitude of its forward velocity is given by, there's the metric tangent components here. The tangent components, as we've seen, are just the forward velocity of the particle, and so we use the metric to contract on the first part of the expression here, u mu, or u mu, I should say, the last part here. And when we contract on that, we find that the magnitude squared is minus c squared, and that's the case always in special and general relativity for a particle with mass. Its forward velocity is parallel transported along this curve, and what that means is that magnitude is held constant. So the magnitude of this tangent vector, as it's moved in incrementally, infinitesimally small steps along the curved world line here, as it's moved along very, very small steps, both the magnitude and direction are held constant. That is what the idea of parallel transport is. The magnitude, this object here, minus c squared, is held constant, and the direction is held constant, and that's what we mean by parallel transport. Now, massless particles travel along null geodesics with the square of the magnitude of its forward velocity given by that thing equal to 0. That's for massless particles. They travel along the null geodesics. Again, they parallel transport the tangent vector. Now, the condition for parallel transport, as we saw earlier, was dt d lambda. Here's d lambda, and here's our object. Here's the components of the tangent vector, and here's the basis vectors. Now, we can replace the tangent vector components. They're really just the four velocity vector components with the same basis vectors. And we know that the total derivative of that, with respect to lambda, the affine parameter, is 0. Alright, so let's just go through the steps why that might help you to see what the steps are. Okay, so we Leibniz rule or product rule here. We differentiate the components times the basis vector plus the components times the derivative of the basis vectors. Now over here, nothing surprising, the derivative of the components here with respect to lambda. But when we come over here, the basis vectors are a function of the position coordinates of the manifold, because the manifold is defined by the coordinates, the space and time coordinates in terms of the space-time manifold. And so we break this derivative up with the chain rule, because the basis vectors are functions of the coordinates of the manifold. So we differentiate the basis vectors with respect to the coordinates of the manifold times the derivative of the coordinates with respect to lambda, the affine parameter there. So we use a chain rule here. Okay, coming over here, du d lambda times that, nothing's changed there. We've got u mu here, components of the fourth velocity, and then the partial derivative of the basis vector with respect to the coordinates of the manifold gives us the affine connection, or the Christoffel symbol of the second kind here, times the basis vector, and we expand that out, beta up, beta down, so that's summed across there, times dx nu d lambda. Okay, some things here, what we can do, the labeling here, we've got a beta up here and a beta down here, we've got a mu up here and a mu down here. It doesn't matter what we call our indices, we're summing over all of them, so we can interchange these, swap these. We could call beta mu, and mu we could call beta. That's exactly what we've done down here, and that allows us to factorize out the common basis, factor out the common basis, e mu here, this becomes an e mu down here. We can, and then the next slide you'll see that we can factor that out. Here it is, out mu, and there are the components, the total derivative of our tangent or 4 vector with respect to the affine parameter. Here are the components, and here's the basis vectors. Now, again here, let's split up u mu, because we know that that is really dx mu d lambda. That's u mu. D lambda of that will give us the second derivative here, and then all the rest over here just carries over. All that times the basis vector, it's equal to 0. Now the basis vectors are never equal to 0. There must be some basis vectors there, because your manifold exists, and so you have basis vectors at all points, and so the geodesic equation becomes these components here set to 0. So this equation involving the components, involving the coordinates of the manifold, differentiate with respect to the affine connection, and that whole expression is 0, and this is the geodesic equation. Alright, the connection coefficients for the Schwarzschild metric are these here. That is the symmetry in the lower two indices. 1, 0 is the same as 0, 1 up here. And these are all the non-zero ones. Okay, these are the non-zero connection coefficients here. The rest are 0. Now, the geodesic equation, reminding you again, here it is. And our coordinates x mu are these, ct are theta phi. And so the geodesic equation is this object here. Now you might notice there's actually a c dt d lambda here and a c dt d lambda here, but you divide through by c, they disappear, so it takes this form here. Just be aware of that. Also notice the symmetry in the lower two indices of the Christoffel symbol of the second kind, 1, 0, 0, 1, they're both the same, and that will show up when we evaluate. The first geodesic equation has the 2 here, because when we look at gamma 0, 1, 0, gives us this object, but then we also have a gamma 0, 0, 1, so a gamma 0, 0, 1, so we have a second one of these. And the end result when we do this geodesic equation is that we end up with two of these, and that's why the 2 is there. Okay. Next one. The next geodesic equation, the second one, and the third one, and then the fourth one. The coordinates have run from 0 to 3. Same thing here, you have t, r, theta, phi, and you have an equation for each one of those coordinates. Alright, next thing now, the magnitude of the fall velocity of a particle with mass is constant along this geodesic. So we have using lambda equals tau as our parameter. This contraction, the magnitude of the fall velocity, using the metric here to contract one of the indices, one up, one down, then we sum over them, is minus c squared. So this is the magnitude squared. I should say magnitude squared up there. And just writing that out, just for the sake of showing everyone here, g mu nu here, sum over the indices 0, 0, 1, 1, 2, 2, 3, 3, all of that goes to c squared. Just reminding you, for the Schwarzschild spacetime, here's the metric. This is the metric. Next one over. Now, if we substitute the metric terms and u0, 0, u0, u0, and u1, u1, if we substitute in from the metric, we get this expression here. Okay, and just writing it out, replacing u0 with dt is c times dt d tau, remember that. u0 is c times dt d tau, that's the coordinate system I'm using here in the video. Here, u1 is dr d tau, u2 is d theta d tau, and u3 is d phi d tau. Okay, and all of that comes to minus c squared. Now, there are some underlying symmetries that will help us solve this. That can simplify this equation, and we know that the Schwarzschild metric is independent of time, and so there exists a killing vector associated with this invariance under time translations, and is a result of the conservation of energy law applying to our particle. And I have some videos on this channel on killing vectors and symmetry and so on. So have a look at those. Going over, our killing vector in the time direction is this one. Okay, and we can use the metric to lower that contravariant index here. We can lower it down to give us the covariant position down here. Our killing vectors are boundary condition at d tau. Our affine parameter is tau this time because we're dealing with a particle with mass. Kt dot u is 0. And so the momentum, now just one more thing, there's two approaches I'm about to use now. The momentum per unit of mass for our particle is P equals m0 u equals u, where m0 equals 1. So if we have a unit of mass, 1 kilo, a unit of mass, we can use P is equal to u there. If our mass, our rest mass, m0 is a rest mass by the way, our rest mass I should say, if it's not 1, then we can simply divide through by m0, here we go, and that gives us, that ends up giving us this object here is equal to the fall velocity vector. So the momentum divided through by m0 here to bring it down to the momentum per unit mass, and will give us equal to the fall velocity. I hope everybody can see that. If m0 is actually 1 kilo, but it's just a unit mass, then you put 1 in there and the momentum vector becomes equal to the fall velocity vector. So the momentum per unit mass is equal to the fall velocity. Or if it's not unit mass, then just divide through by the mass, the rest mass of the object, and you'll get the same result. Alright, next one. So dd tau of this object is dd tau of that is equal to 0. Let's substitute in here. Kt is g00 k0 u0. Alright, is dd tau of that is dd tau of this object here, and it lowers the index. Now, dd tau of g00 of that is dd tau of, from the metric, we get this. This comes from the metric, the g00 component, and u0 is c times dt d tau. And we get over here dd tau e on m0 c. Alright, next thing is from which we get the, now from here we can see, if you look here, dd tau here, dd tau here, look at what's in the brackets here. You have this argument here, this one in here, and so we can say that the e on m0 is this object, multiply that c across, because what's inside the brackets here is equal to what's inside the brackets here, and so we have the total energy per unit rest mass, e on m0, the total energy, that includes everything. The total energy per unit rest mass is this object here, total energy per unit rest mass. Next bit. Now we can interpret E on m0 for time-like geodesics as the total energy per unit of rest mass, including any potential energy of the particle as it travels along the given geodesic, and that's according to a static observer at infinity. Now, why is the observer so distant? How do we know it's the observer at a distance, at infinity? Well, looking at our definition of the forward velocity of the particle, we see that some distant observer in a frame S sees the particle in frame S prime passing by with some gamma factor and ascribes a following forward vector to it. Now, this comes from the video I made on forward velocity. If you have a look at the video on forward velocity, you'll see the frame S prime, and how they're related in terms of how an observer in S observes, not sees, I should say, observes, measures, not sees, the particle in frame S passing by. And this is the forward velocity that observer in frame S ascribes to it. There's the gamma factor as frame S prime is passing by. That's might be helpful to think of it that way. So you can see here's an observer at infinity looking at this object and ascribing this forward velocity to it, and then all the previous calculations we saw. We can make use of another killing vector in the Schwarzschild geometry that reflects the conservation of angular momentum in this space-time. Here's one in the phi direction, the azimuthal direction, this object here, and again let's go through the same thing, k phi dot m0u, dd tau that object, dd tau this thing here, and is equal to 0 as we saw, because that was a condition. dd tau this is 0, and that tells us that this object here is equal to the angular momentum divided by the rest mass of the object, and we know that this is constant because the antiderivative of all of this means that this object in here is equal to a constant. And so we anti-differentiate that. And that constant is the angular momentum, which we'll call L. We'll label that L over m0. That's the angular momentum per unit rest mass, and that's constant. Okay, so just reminding what we've achieved so far, we've got this object is equal to this from earlier, and also we have this object equal to this. And that comes from our metric and from what we've done so far. Alright, now returning to our forward velocity, here it is, just reminding everyone, there it is all again. Now, let's substitute in everything we had on the previous page, and we go over here, dt, d tau all squared, and that gives us this object here, times, and gives us this object. Don't notice the -1 here to the power of -1. That wasn't the case up here. And then over here, this stays the same, this bit stays the same, and we have, in this part here, we substitute in, and we get this object here, the angular momentum. Okay, so we've reduced down to this forward velocity equation we started with, and we've reduced it down to this form here. Okay, well, let's have a look, what else can we do? Okay, now, how about we go to the equatorial plane? We set the polar angle theta as pi on 2, and because we're fixing, there's no variation in theta, there's no change, then d theta is 0. And so that's going to drop out of the equation and give us here. Here we go, so in the equatorial plane, restricting our motion now to the equatorial plane, we now have our equation is simplified a little bit further, and we can rearrange that if we want to get dr d tau by itself. We can start taking this here on the other side and this bit over there on the other side, and we get this expression here. So here's the equation here. Now, go further, multiplying through by the inverse of this object, and we'll come out with this object here. So here's our equation of motion for this particle of mass m0, and it's in the equatorial plane. And okay, so let's move on. Alright, now for purely radial motion, we're going to set d phi, d tau, equal to 0. So that implies that the angular momentum from what we saw earlier, if d phi, d tau is 0, then the angular momentum disappears as well. Okay, because we want purely radial motion now, and that gives us an even simpler equation. Dr d tau all squared is this object here. Alright, it's looking a little bit simpler, isn't it? That's r, the coordinate. This is tau, the proper time. That's the time measured by the particle carrying its own clock. Alright, now we can go further by differentiating both sides with respect to proper time. So d tau of that equals d tau of this. And you'll notice these constants here will disappear when we do that. And so over the next page, we end up with 2 times dr d tau times d2 dr d tau squared. d tau of this object here, and when we differentiate that, use the chain rule, we have minus 2 gm on r squared times dr d tau, and then what we can do is divide through both sides by dr d tau, because you've got dr d tau here and there, and also we can divide through by 2. So when we do that, we end up with d2 r d tau squared is minus gm on r squared. Okay, Now this result gives us the acceleration of a massive particle in a radial direction in a Schwarzschild spacetime. It looks obviously very similar to the Newtonian version, except that the coordinates have a bit of a different meaning. This is tau, the proper time, as measured by the particle carrying its own clock with itself, and this is a coordinate value. It is not a physical distance or measurement. You have to be careful. Coordinates are not physical measurements of distance or of time. To do that, you need to involve the metric to convert them to physical units of measurement. So these are coordinates, whereas in Newtonian mechanics, these are distances. So there's a different meaning here. In relation to coordinates, let me leave the last word on coordinates to Einstein himself. And there you go. That's the end of that.